Hey, how's it going? Before we jump into the content, I just want to take a minute to thank you for stopping by the channel and checking out the content. If you like this content and you want to support more content like it, then make sure to subscribe to the channel and like this video. You can also check out the YouTube membership program and cybertrainingpro.com, where I put practice exams and other things that I couldn't put on YouTube. Again, regardless of how you support the channel and my content, I couldn't be more appreciative. Thank you so much, and let's get into the content. Routers are a piece of hardware or software that forwards packets based on their destination IP address. This means that routers operate at the network layer or layer 3 of the OSI model. Now, routers are typically dedicated boxes that have 2 or more connections. For example, you might have your internal network connected in one port and then the internet on the other port so that traffic can be routed between the 2 networks. Devices like Cisco routers are going to have a console port where you can connect directly into that command line interface for that router and set up the initial configurations, or if you need to come back and configure things later. You might be familiar with the internet router that you have at home, but unlike dedicated boxes that you have in enterprise networks, these home consumer devices typically will have other functionality included in them, like switching, wireless, and firewalls. There's special switches that can operate at multiple layers of the OSI model, and we call these multi-layer switches, or MLS, and specifically switches that can do routing are called layer 3 switches or layer 3 capable switches. As we've discussed before, layer 3 deals with IP packets, so anytime that a router receives data, it will first strip off layer 2 information so that packets can be dealt with as they're received. Next, the router looks at its routing table, which identifies the networks that the router knows about so it can decide where it needs to send that packet. Now, on the screen is an image of a routing table on a Windows system, and we have the destination, the net mask, it might also be called a gen mask. You might have flags, metrics, and the interface where traffic needs to be sent out of. You can get similar output to this image on a Linux system using the IP route command or netstat-r on Mac OS and Windows systems. Depending on the type of system, you might have different labels or additional columns, but these are the major ones that you need to know. When you're looking at the routing table, zeros mean anything. So for example, we see a network with 65.0.0.0 with a subnet mask of 255.0.0.0. This means that anything can be in the last 3 octets of the IP address for that rule to match, because this is a /8 network. A common entry that you might see is a default route or destination network of 0.0.0.0, which means any packet that doesn't have a corresponding entry will follow that rule. We also see our address and the loopback route in addition to the 127.0.0.1, which is our dedicated broadcast address for all computers on the same network ID. We have 224.0.0.0, and this is the multicast address range. And we have 255.255.255.255, which is a limited broadcast, and that will reach every node on the local network. If you see an asterisk for the gateway, or in our current image, we have the on link, this means it's our local network destination. So we can use ARP to grab the MAC address and send the data onto the destination. With the metric column, this is basically a desirability measurement for a route, just in case you have multiple routes that want to reach the same destination. Lower metrics are always chosen first. One of the nice things with enterprise routers is that they tend to have modular functionality. This means that you can add modules specific to what you need, and that opens the door to using other technologies like LTE or data over cable service interface specification or passive optical networks, just to name a few. In this course, we've discussed the issue with IPv4 addresses and how they're not available for everybody to use without approaching your internet service provider specifically to purchase or lease one. Well, if we can't get them, how do we route the traffic to the internet? Network address translation, or NAT, is a technology that allows us to take internal traffic and use a single public IP address to route that traffic. Imagine on your home network that you have 5 computers that you need to connect to the internet. With NAT, you use your router that connects to the internet as a default gateway for all the computers and have it perform NAT. Now when traffic for the internet is sent through the default gateway, the source IP address is changed to the outside interface connected to the internet. Now, one issue with NAT, though, is that you need enough public IP addresses to actually translate the traffic out, because every session needs its own IP address. Dynamic NAT, also known as pooled NAT, allows you to provide several IP addresses that can be used for NAT, but there's a better solution. Port Address Translation, or PAT, is a one-to-many connection technology version of NAT. Now, PAT uses port numbers to map traffic from specific machines on a network. PAT addresses the one-to-one limitation of regular NAT because there's 65,535 port options to use for tracking network traffic. Another benefit of PAT is that it disguises your internal network host from the dangerous internet. Remember, with NAT, the IP addresses change the outside interface of the router. Well, with PAT, the router might actually also change the port so that when it returns, it can reverse that process and look into its NAT translation table to determine where that return traffic needs to go. One thing to keep in mind is that typically when you hear somebody talking about NAT these days, they're most likely talking about PAT unless they mention a one-to-one relationship. PAT only works for outgoing traffic, but what about incoming traffic? A good example would be if you have an SSH server or a web server on your internal network that traffic needs to get routed to. Port forwarding allows you to designate a specific local address for various network services. So if a host tries to access port 443 on our public IP address, our router examines that request and it knows where to send it. Both PAT and port forwarding are easy to configure on consumer routers, and even on enterprise equipment, it's not that difficult, but it does require a little bit of work. We haven't talked much yet about how routers learn about different networks for routing traffic, so let's shift gears. There are basically two ways that routers can learn about networks. First, they can have static routes that are manually configured by us, or second, they can also have dynamic routes that are learned from dynamic routing protocols, which means that if something changes, then the routes get updated automatically. For example, if a connection to a statically configured route goes down, do you really want to sit there and have to troubleshoot it? Of course not. These protocols can communicate both if routers are directly connected to each other or even if there's multiple hops between routers. There are three groups of routing protocols that you need to know: distance vector, link state, and hybrid. Before we dive into the routing protocols, let's talk real quick about the metrics that routing protocols use. Now, routing metrics are a value that routers use to compare routes when there's multiple paths that traffic can take, and the lowest value always wins. These metrics use several criteria to determine their value, and you might actually hear these values called metrics too, but don't get confused. The possible criteria include one or more of the following. So a hop count, which is the amount of routers that packets have to go through to get to their destination. Bandwidth, because some connections are faster than others. Delay or latency to communicate. And cost, which is using connection with bandwidth speeds for some protocols. Okay, now that we have that done, let's start talking about the different types of routing protocols that exist and that you need to know. Distance vector routing protocols really focus in on how far or how many hops traffic has to travel through to reach its destination. For example, if traffic has to go through one router outside of its network, the hop metric would be 1. If there were 2 routers, the hop metric would be 2, and you get the idea. It just keeps going from there. This is where the metric setting needs to be set based on the speed of a connection link. The process works like this. Distance vector protocols send their entire routing tables to other routers that they know about, and eventually all the routers will know about each other. Once the routers know about all the paths, they're likely going to have multiple entries for the same network. So they keep the lowest metric path and they delete the duplicates. With distance vector routing protocols, they'll keep repeating this process, but if everything is the same, the tables won't need to update. This is a steady state that we call convergence. As you can see from this explanation, distance vector routing protocols aren't great for very large networks because they can take a while to initially share information, and then if changes happen, they're very slow to update. 2 distance vector routing protocols that you need to know about are RIP version 1 and RIP version 2. And the path vector that you need to know about is BGP. Let's talk about these protocols. The Routing Information Protocol, or RIP version 1, is the original distance vector routing protocol, and it goes back to the 1980s. It has a maximum hop count of 15. Updates are sent out every 30 seconds, which is a problem because every router sends out their routing tables at the same time. RIP version 1 didn't know how to use variable length subnet masking, so you couldn't use different subnet masks. And if it wasn't bad enough yet, RIP v1 didn't have authentication mechanisms, so attackers could send false routing table information. RIP version 2 was adopted in 1994, and it works similar to RIP version 1. RIP version 2 did have some additions though, and those additions include that it supports variable length subnet masking. It also includes authentication built into it. It swaps broadcasting for multicast addresses, and it changes the update time frame from 30 seconds to 90 seconds. Again, even though RIP version 2 has some additions, it isn't great for large networks, but you might be able to get away with it in small configurations of say 2, 3, or 4 routers. BGP, or Border Gateway Protocol, is what you'll see on edge routers in your organization, but it's especially common in internet service providers or massive organizations like Google. BGP uses autonomous systems to share a unified policy regarding how traffic is exchanged with other autonomous systems. These autonomous systems require an autonomous system number, or an ASN, assigned to it by the IONA group, consisting of 32 bits. BGP is considered a path vector routing protocol, but it's also considered an exterior gateway protocol, or EGP, and CompTIA refers to BGP as a hybrid protocol. BGP uses route aggregation to simplify what it actually stores in its routing table instead of storing the entire internet. For example, when traffic is being routed, your router might know that the traffic is destined for a certain provider or a country, but it doesn't need to know the specific state or the city. Link state protocols were created because we needed a faster and a more efficient routing protocol than RIP. And the main idea is that individual routes should be updated as they happen or they appear. The two that you need to know about are OSPF and ISIS. Open Shortest Path First, or OSPF, is the most commonly used interior gateway protocol in the world. It converges almost immediately, unlike RIP, and it works within a single autonomous system. The OSPF process works like this. Routers send out hello packets looking for other OSPF routers. When two adjacent routers form a neighborship from hello packets, they start to exchange link state advertisements, or LSA packets, throughout the OSPF area. OSPF uses cost as its metric related to how fast the connection link is, and the lowest total cost is calculated for routes. This means that the path might be longer, but the speed's quicker. Again, OSPF uses areas to group routers together, starting with the area ID of 0, or 0.0.0.0, and it supports authentication. The intermediate system to intermediate system, or ISIS, is the only option when it comes to link state dynamic routing protocols. It's very similar to OSPF because it uses areas and it only sends updates to routing tables. The big advantage of ISIS is that it worked with IPv6 from the start, but it's not very common in the real world. The Enhanced Interior Gateway Routing Protocol, or EIGRP, doesn't really fit into either distance vector or link state routing protocols, and it's more like a hybrid. But if you have to choose on your exam, I'd go with it being a distance vector protocol. EIGRP was developed by Cisco before OSPF, and it replaced their first iteration called Interior Gateway Routing Protocol, or IGRP. Now on the screen, you can see a summary of the dynamic routing protocols that we've covered. Outside of the general differences between the protocols, make sure that you understand that BGP is the only exterior protocol, because that's a likely question. And I would highly recommend that you study this chart in and out and make sure that you understand it. Now that we've talked about different routing protocols that exist, you might have some questions coming up, like can we mix and match routing protocols? Or can we share information between the routing protocols? First and foremost, the different routing protocols can't directly talk to each other. For example, we can't be running OSPF and have it directly talk to EIGRP. Fortunately though, we can have multiple routing protocols running at the same time, and we can use something called route distribution to share information that we learned from one routing protocol with another. We know that a router using a single routing protocol can use the metrics to compare paths, but when we have multiple routing protocols, our router will use something called administrative distance, or route preference, to choose the best path. The complexity of routers, switches, and other network gear varies greatly depending on the type of equipment. For example, a home consumer grade router, which is a great example of an unmanaged switch, will be simple to plug everything in, power it on, and log into the web interface, or it'll just work. They also make small business gear that operates this way called SOHO devices. Now, enterprise grade hardware, also called managed devices, like the kind you'll get from Cisco or Juniper, will require some additional steps once you unbox it. Some of this equipment does have a web interface that you can use, but we'll walk through a quick command line setup right now. The first step with this kind of gear is that you're going to need a console cable, which is also called a rollover cable or a YOS cable. These cables can either plug directly into a serial port on your computer, or you can use a USB to serial adapter and connect the two cables together. So I want you to be able to see what these cables look like. So this is what a serial cable looks like. You can see on one end, it has kind of this RJ45 looking plug, and on the other end, it has a serial cable connection. And then this is what the adapter looks like. So you have your connection where you actually plug that serial connector into, and then you have a USB connection on the other side. Next, you need a terminal emulator program like PuTTY or Secure CRT to connect into that device. The common settings that you'll need are 9600 baud, 8 data bits, 1 stop bit, and no parity bits. On the first boot up, your device should have an initial configuration to walk you through, but these devices also allow you to enter everything that you want. Now you'll be able to connect to the device. And at this point, managed devices tend to have their own specialized operating system. For example, Cisco has iOS, but this isn't like iOS on your iPhone or your iPad. Don't worry, for Network Plus, you don't have to know specifics of how it works. When you actually get into like a Cisco router, if you type enable or EN, you'll enter privilege exec mode, which allows you to run a lot of the view only commands or show commands. Next, type configure terminal to enter the configuration mode. You can also type CompTIA, so CONFT. Enter into an interface using the interface FA0/1 command. Now configure the IP address using the command IP space the address, so 192.168.1.5 or whatever you want it to be, and then space 255.255.255.0 for your net mask or your subnet mask. Now type exit and save all your configurations using the copy space run space start command. As networks grow in size, we need more efficient ways to manage all the devices instead of logging into a single device's command line or its web interface. Network Management Software, or NMS, is a specialized software that can talk to all of your routers, switches, and any other networking devices that you have in one location, which is typically a website interface. Now, usually there are two types of network management software. You have software that's developed by the manufacturer themselves, like Cisco's Configuration Professional, and then you have software developed by third parties, like SolarWinds. Functionality is going to vary on the software, but typically third-party software needs a little bit more configuration. When it comes to routers, they don't typically fail, so troubleshooting them shouldn't be the first option. If you have routing table issues, you might want to look at static routes if you have any configured. Are they configured correctly? Is the subnet mask correct? And for dynamic routing protocols, are they getting the correct route information? If not, there might be a convergence problem. You might also want to consider the maximum transmission unit, or the MTU. We know that if packets are large enough, they might need to be broken down or fragmented into smaller chunks in order for them to be sent. Unfortunately, sometimes receiving systems have a specific path MTU that describes the largest packet that system can receive without fragmentation. And that means we either need our devices to have the MTU value set correctly on our sending system, or we need to use path MTU discovery to actually find out what that value is. The main tools that you can use for router troubleshooting are ping, route, traceroute, MTR, and path ping. We've already covered ping and route in this course, but if you remember, ping helps you reach other systems, and route actually manages the routing table. Traceroute on Linux and some other networking gear, or traceRT on Windows, will show us the path the data takes as it's sending from one system to another. For example, if we know the data needs to go through 3 devices to reach its destination, but it stops after 1, then we can identify that there's an issue with that one router not letting traffic through. MTR only works on Linux, and it's similar to traceroute, but it continually updates the routes that you've entered. Pathping is a Windows alternative to MTR, and it'll compute the performance over a set time and show you a summary at the end. These tools use a default time to live, or a TTL value, that decreases by 1 after every router that it goes through until it reaches its destination. It will also stop if it hits 0 so that packets don't keep going on forever, and then the final router discards the packet and sends an ICMP message to the original sender. You can set a specific TTL value with these tools if you really want to, but I'm guessing in most situations, you're not going to need to.